Hello, everyone, and welcome to the fourth Func Prog Sweden meetup. This time we're live streaming with a small audience and live to you. The first one we had was actually live. Second and third we had was like on Zoom, and now the fourth is live streaming. So we're trying out this, and let's see where it leads us. Yes, the agenda for today then is. Oops, sorry. Yep. So we have a short intro, that's me. And then we'll have the first presentation by Henrik Feldt, Patterns of Functional Programming. And then we have a second presentation, C++ for Functional Programmers, by Harald. And then I'll do a short summary in the end. Yes, so why did I start this meetup group? Well, because we love functional programming. We are open and inclusive. We like people to be part of the community and to learn functional programming. We like to share, so this is also why I started this community, to share, like, how do you get started with functional programming, or how do you develop advanced stuff with not functional programming languages like C++. Yeah, so let's have fun and share and spread functional programming. And this time around, we have a venue sponsor from Funnel. So I'd like to say thank you very much, Funnel, for having us in your office and sharing your office space. And I would like to introduce Ville, who will say a few words about Funnel.
Thank you, Magnus. Funnel is to data like sanitizer is to your hands, makes it clean and ready for use. Please check out our product and ourselves at funnel.io or jobs.funnel.io. You can find us. We love functional programming, of course, I do. I'm part of the CTO team at Funnel and very much happy to have the meetup here with us.
Thank you very much, Ville. Yes, then if you want to be your speaker or sponsor at the meetup, just ping me. You can find me at Meetup. You can find me on most social platforms. If you have a venue and you want to share that for a meetup, again, please ping. We are always looking for venues where we could maybe try out live streaming in your office. So just contact me or the other organizers, Matthias or Tien. And a short how-to for today then, because we are live streaming this event. So it's the first time we live stream, so we have zero clue how to do this. So we are starting up. Questions in the room, please, presenter, repeat the question so everyone on the live stream knows what the question is. And if you have a question on the live stream, please ask them through the chat in YouTube, and I will read them up as we go along. Yes, so let's start the fun stuff. First presentation is by Henrik Feldt, Patterns of Functional Programming. Thank you very much, Henrik. And now we'll switch computers for a while. Yeah.
I got some reverb going on here. It's a bit of a party trick. Just go close to that one and see if it doesn't like me. Maybe we can turn this down a bit. So welcome. It's still loading here. I think it's the screens that are loading. So I'm presenting on design patterns in functional programming. And the sub-theme here is it's not about monads. First of all, me. Right now I'm working on this new product called Behavioral Analytics with Logari Analytics. Behavioral Analytics, basically the business idea I'm trying to create is to model user segments and user behaviors using causative analytics, and then highlighting both what you can do more of and what you can do less of in order to improve your key metrics.
So Logari Analytics is actually initially a software product written in F# for logging in functional programming languages. So a few of the examples tonight will be about this library. Now, the product I'm building is actually a separate application, but this is still free and open source. I have some background in building software. I built some functional web servers. You see the Expecto library out there. I help people with cloud migrations and so on. But back to what's a design pattern and what we're going to speak about tonight. I'd say it's a construction that repeats itself because it's useful and it fits the situation. And also, you could divide them into these, especially when you write functional programming. Parsers and validations, state and handling of state or state mutation, control flow, and this is actually what Haskell is so good at. And then you also got the sync await in Python with Twisted and C# and in TypeScript and JavaScript. And then you got higher order functions, which is very often mentioned. And the other thing that's mentioned, of course, is monads, but I'm not going to go into those. Let's say that monads are nice for control flow when you want to write imperatively, but most of the time you are already writing in an imperative language, so you may not need them. So I was thinking of some interesting patterns that you could use, and I thought of these. You have the delegator pattern, for example. Of course, when you look at design patterns, you have the original Gang of Four book, but it's very old now and it's very much geared towards object orientation. In functional programming, you often have this hole in the middle, which we'll dive deeper into. There is one called state machine. So state machine in object-oriented programming is modeled using a lot of classes. But in functional programming, you can actually do it quite nicely with mutual recursive functions. I'm going to show an example of that. Then you have currying. This is like the workhorse of any functional program, because you curry all the time. You curry basically everything that you inject into your app as configuration. And it's also very much used for memory management. Then you have dynamic configuration via a closure, and alternatively via a construct. And 3, I'm not going to go through: continuation passing style, scans, reductions, and so on, which is part of the higher order functions. And then different sorts of observables, jobs, promises, tasks, you name it. So let's start with this one, hole in the middle. And I must encourage you on YouTube to just ask questions, and also the audience, you may have to seed some questions here. So I'm counting on you. Hole in the middle here is when you want to reuse a complex function implementation. So let's look at an example. Let's pretend Colorize is a very complex function. In this case, it's moderately complex, but you can easily imagine setting up many different things in something that fetches data from an API, such as API tokens, maybe permission handling, looking up what roles you want to send, maybe computing the different query strings you want to attach, and so on. All of these things is something you probably want to do in at least not too many locations inside of your application. And that's why then you can use hole in the middle. What it gives you, the first arrow up here, is something you can pass in, a callback, which then configures the complex thing. What it configures has already been configured to some extent by this complex function. In this case, the complex function is the async that you see on the second bit with the second arrow. And we're calling our config callback to be able to inject more headers or inject more things. So you can say that use this pattern when you have an implementation that's sufficiently advanced and you don't want to leak that complexity into the surrounding system. So then the way you can use this is by having a call to Colorize, and then you pass in the local, the contextual data, which you can't otherwise access inside of your complex function. So for example, if the user has typed something in, like 0, 1, 2, 3, etc., local to page, then that's not something that your complex function will know about. So you want to reconfigure it where you call it. And that's when this is neat. The astute listener might have noticed that we're also using currying as part of this example. And this is different because the previous was when you wanted to reuse a complex implementation. Currying is when you want to reuse a complex setup. So back to the same example here, you can see that Colorize actually returns a function that takes an item and returns a promise of colorized item. So its first parameter here, and this is TypeScript by the way, is configure. So configure, once inserted into Colorize, gives you back another function that you can pass around, a function which is now pre-configured, so to speak. It's configured with a configure callback. And just between these two lines, between the two red lines, you can do arbitrary computation. You can think of currying like when you pass the first couple of arguments, your configuration, maybe your context object, you can do arbitrary lookups, arbitrary calls to web servers. You can pre-compute a cache. You can pre-compute computations that yield results. And then you return some function which uses all of the things that you've already pieced together. So you can see them as a way of constructing or constructors. And in this example, then getColor is the end result function, which we can then use to get color via this API call. So you can say that part of the cost is taken when you execute this. But when you later call getColor, then you don't have to pay the upfront cost anymore of pre-computing the way the function should behave. So that's when you want to use it. So let's move into more advanced territory. We got something called dynamic reconfiguration. In a distributed system, this could be, for example, if you have a set of Kafka brokers and you want to dynamically reconfigure what brokers you send to based on their uptime or based on their liveness. Are they responding to my calls or not, basically? But because you write functional programming, it's not necessarily easy to change things on the fly because everything is basically meshed together into this continuously executing function body that keeps on executing. So you want somehow to inject non-determinism, somehow to inject configuration in there, right? So in this case, it's F#, and I'm taking an example from Logari, the logging library that I'm now building an app for. And you can see the default configuration on line 19, which sets up, well, what it says, default configuration. And then I'm using this abstraction called Dvar for dynamic variable. This is different from the Haskell Dvar for concurrency. This is just basically an Excel shell, an Excel cell, which you can then compose together with other cells. And then at some point, you want to use your composed value in a context. So this would be the instantiation. And you can see, for example, Dvar create at the bottom bit, where you take in the default config as a value. And you can see the default config is actually a static, non-changing value. But Dvar makes it mutable, so to speak. In classical object-oriented procedural, rather, languages, you quite often have that you have global variables, but those variables depend on each other arbitrarily. So at any point when you have more than one or more than two, you have to keep that in mind when you update them and recompute all of the dependents as you go. With this, you don't have to. I'll get back to the implementation. So this is a Flyweight. So in the logging library, you want to be able to get loggers from when your app starts. But by then, I haven't configured like the sending and the exporters and targets and the pipeline and everything that you have in a logging framework. So I'm just giving back a Flyweight. A Flyweight is the design pattern as well, something from the Gang of Four, in fact. And you can see here with F#, you can mix and match object-oriented programming with functional programming. So on the second line, you can see that I take the configuration Dvar and I map it so that in the callback, I'm gonna actually break the rule here and move towards. You can see here that you get the config value, the actual current value, which you can then invoke functions on. And that means that you can compute with the most recent value. So now you have an expression, Logari, which is a function expression of, no, sorry, it's not a function expression, it's just a Dvar of logger. So that logger will now always be up to date with regards to your configuration. So when the configuration changes, this one changes. And that means you have your suppleness. If you remember the DDD book, it's like a leather jacket. You want it to be supple in the right bits. And this is to be supple in the right bits because now I only have to care about whether I have the right type of dynamic variable. And if I have that, I can be absolutely certain that dynamic variable is the very latest value up to date. And then in log with ACK, I'm getting the value from this Dvar and using it. So the implementation can look like this. It has some mutable cell, something you can update. And when you update the cell in the put down there, you want to atomically switch it out. So this is very similar to Clojure's atoms. Correct me if I'm wrong.
Do you mean that you partially applied the function with a dynamic value, and therefore the function is dynamic as well?
Which function did I apply?
The previous slide. There,
This
when
one.
you did let logger d equals config d.
Yeah, so I'm picking out the config d, and I'm creating this expression that listens to the event. And when the event triggers, I run the callback with a new value that I got from the event and recompute the value inside of my own cell. So in this cell, I got a logger. So whenever config d changes, I rerun this. And that's just a function as well. Map is just a function. It's a function that closes over whatever parameter it gets in. And then calls it when the config changes. And then you have some new value in your new cell. So you basically instantiate this one, Dvar, for every new value you get. And you chain it back up to the root. It's a nice pattern that you might find useful. All right. Let's move on to the machines. Yeah. Audience. Yeah, all right. Mutually recursive function as a state machine. And now I'm like, yeah. So that's when you want to separate runtime states from each other. All right, let's have a look. Again, from Logari. So in Logari, we want to have multiple targets. They have different initialization, different failure modes, different ways of managing when, for example, you get too much logging going on, or they write too slowly, they consume from you too slowly, etc. So one way of managing that is to have a state for each of the cases that you might have. So we got loop here. Loop itself just declares, well, either you can say it's one function for all of this, or it declares init, running, checking, rotating, recovering as functions themselves. These corresponds to the lifestyle that you want your file logging to have. And you can see that it takes a file configuration at the very left. And that's, again, currying. Will is a way to recover when it crashes. And then some API. So also just above, you can see that it then returns a job of unit. So this is F#. That means that it's implicit what the function returns. But you can imagine, like, if you were writing C#, you'd have to declare a job unit out here to the left, to the right. So that's something you can then execute asynchronously, or rather with green threads. But back to the state machine. So first of all, the function is declared, and at the very bottom, it's then called. And that kicks off the configuration, which returns a job. Maybe you can run things before you return the job, or maybe you want to run them inside of the asynchronous computation that you then hoist onto a scheduler in Threadpool. But the running state here is one that I wanted to show you because it shows the transitions. What's a state machine but transitions between states, right? So in the running state, we might go and we might get a signal on the channel called shutdown. And then we simply want to shut down the state. Now, this is a bit mind-boggling because both the state I pass around the state machine and the state machine itself has states. But in this case, shutdown state means dispose of my connections. And then I'm just acting the return, let's call it promise that I get in the ACK. And then I'm not doing anything else. So F# is indentation sensitive, and I don't have anything after API shutdown channel. So that's basically returning from my concurrent job. But in the rotate channel just below, you can see my to-do there, but I'm going to the rotating state. And that means that I don't listen to the shutdown command anymore. I don't listen to the logs and the requests and the metrics coming in here anymore. I only now want to do the rotation of files. And because I'm potentially getting thousands of messages per second, it's pretty nice to just say, I'm not going to pull that channel anymore. In this state, I'm only going to rotate the file. And by calling into the rotating state, even though all of this is a concurrent job, something that executes on green fibers, you don't actually have to have any synchronization primitives in there, because it's enough that you have one job, one green thread of execution, and you change its state. That's enough to synchronize with. And the rest is just signals coming on channels, like you can see at the top and further down. So similarly, once you've written, you want to check if you've gone overboard and written too much logs into the file, for example. And if something goes wrong, you have to crash, basically. So this is what the state machine could look like. Do you have any questions on this? All right, then I just wanted to give you some more resources that you can look at. I know Haskell.org isn't a good visual link, but if you click this link in the PDF I have online, you can go to github.com/HAF, and then you find this presentation there together with the sample code in TypeScript I showed you. And you can then also click these links inside of the PDF to find different patterns and different ways of writing. And like my writing style is not to use too many monads, monoids, etc. There is also a very nice blog entry by Alexis King, one of the committers on Hasura in India, called Parse Don't Validate, which is about the way that you do control flow when you want to validate. So instead of then just having your ordinary if this then that, you can actually build everything into a parser. So nice nuances there. And then of course you got some keywords you can search just for finding more interesting patterns in functional programming. So thank you for listening.
Yeah, I have a question. We haven't got any questions on the chat yet. If you have any questions, please ask them in the chat. I have one question. What would you say is the most useful? You showed some different patterns here. What is the most useful pattern to learn?
So these I think are very useful. All of these. The most useful. Well, currying.
Or the easiest to learn.
Oh, the easiest is probably currying. You pass one variable in, you get a function back, and that's it.
Yeah. And what's the most useful? What do you use every day? Like I'm coding every day. Now I'm using this.
Well, I'm using currying every day.
Yeah.
And I'm using reduce or fold every day. And I'm also using the async pattern every day. So I'd say those maybe. The hole in the middle is primarily when you're writing the software architecture for an application. Then you write that in one place, and you do maybe in React you do a higher order component which just attaches it into your rendering pipeline.
Yeah.
And then you don't write it anymore. So you can then not have everyone do that because it's harder.
Yes, we don't. We have a lot of claps, people sharing.
Okay.
Yeah.
Woo. Okay.
Yeah, I have one more question.
Yeah.
As we have some time over now. I mean, I guess you started a program. What did you start with? What language got you brought into programming? And how did you end up here in functional programming?
I started with BASIC.
Mm. Yeah, that's we have some people sharing here.
So I'm not sure that's representative of a functional programmer, but it's something to start with.
Yeah.
So I learned how to do goto and line numbers, and quickly realized that it's not scalable to write those line numbers all the time. I didn't even have an editor to write them for me. I had to type them out. But that was not for very long. But then I went into ASP, a VB script, and VB, and VB.NET, and C#, and then JavaScript, and F# and ActionScript, and a couple of more. So it's been a very crooked journey, but it ended up in a good place.
Cool. I started myself actually with BASIC,
Mm.
and then ended up in Erlang, and then leaving software programming. So maybe that's not a good good example.
That's a final state, Erlang. If you go there, you will become too bitter and must leave.
No, don't say that.
You know I only speak the truth.
Okay. Anyone else have any questions? No? No? Then thank you very much, Henrik,
Thank you.
for your speech. Yeah. Yeah, you want the 5 minutes? Yeah. I'll just tell the people.
Tack.
Yeah, thank you. We'll just, let's see. The screen is rendering. It's using BASIC. That's why it takes time. Go to line 10, go to 20. You got a good question? Yeah. Go for it.
Can you turn me back on? Yay. Okay, so we got a question here. Care to discuss how to approach state machines with distributed processing? The state varies to be passed around or even persisted over time. Right. Yeah, that's a big question, and it's a fun one. So to start out, what's a state machine? Of course, it's something that takes a state and it takes an input and it returns a state. It's a melee machine. And in distributed processing, you have the problem that the processes, they fail. And when processes fail, you need to be able to recover. And then you have different primitives to do that. Then you have algorithms like view-stamped, view-stamped replication, or you have consensus protocols, which are built on logs, write-ahead logs, vals. So the general pattern you do is that you take some input from the network, you deserialize it, then you have your state machine running, you give it to the state machine, you give it some ACK or NACK so that it can reject or accept the message so that you know on your networking layer when to send it out. It does its effect, and then it has some output state. And then it writes that to disk. And it also must write, like initially it writes to the write-ahead log, and then it updates its own database. And then it acts to the network. So you got 3 different moving pieces. And when it writes to the write-ahead log, then if It crashes, it resumes, it reads the write-ahead log, it applies everything on the 2 subsequent steps. If it crashes during writing to its own database and it completes, that's fine. Then it gets resent and you have to be idempotent. And if it writes to both, but it doesn't ACK, then again, idempotent. And if it does everything, you're fine. But that's just for one process. Now, if you want to replicate it, you also need the atomic broadcast primitive. And that means that you want to make sure that every process receives every message at least once, preferably in order, but you don't have to. So if you don't have order, you have to do sequencing. So you have to do a sequencer at the receiver. If you want to be linearizable, you need to have idempotence. And then when you get the message, you apply it like I just said, and then you broadcast back. And the ACK itself can either be batched or singular, but the point is that you need to have at least a quorum understand that the ACK has gone through. So then I recommend looking at Diego's work on Raft, and you can look at the different implementations, etc. D, you got Consul, has its own implementation, and so on. So they go through it really well in their presentations. There's also, I don't remember the name, but something called raftexplainedvisually.com, something like that, where you're basically stepping through the protocol to understand how everything works. So given that all of this works, the stuff I just described has the problem that you have asynchronous systems and they can drop messages. And that's why you need atomic broadcast. So that's something to look up as well. There's also Peter Ballis you can look up. He has a lot of good stuff written on state machines and distributed systems. And I think I'm going to stop there. So that's how you do it.
Thank you very much, Henrik.
Thank you.